Hello everyone, in this video we will design a distributed message queue like Apache Kafka or Amazon SQS. A distributed message queue is a software system that stores and delivers messages between components in a distributed system or microservice architecture. Usually we have some producers who send some message over the network to a message queue. Then we have some sort of consumers who basically pulls the messages out of the queue. And in this lecture, we will try to see how we can design a distributed message queue. Let's talk about the APIs we need. If you have used Apache Kafka or Amazon SQS, maybe you already know. In the beginning, we need to create a queue. For that, we need a create queue API. After that, we need an API like send messages where we will send the messages, and the consumer need another API for reading the messages out of the queue. There are some other APIs we can think about like delete messages and set message visibility. We will mainly try to focus on the first three API today. What is the simplest architecture we can think about? We have a front-end service where basically our producer or consumer hit for all the APIs. Then the front-end service basically passes the request to our backend service where we do all the calculations. Say for example, the backend service basically stores and processes the message in local file system. Then some information we need to store in a persistent database. Say for example, queue metadata and other things we store in database. Let's try to scale a little bit. We are thinking about a very large scale solution where we will be receiving a lot of API calls, right? Definitely one service or host is not good enough. That's why we will kind of create multiple instances of our front-end service. Say for example, here we have 1, 2, 3, 4, right? So if we have multiple instances, that means we need to place a load balancer in front of our front-end services. So we will place an internet facing load balancer where our producer can hit, right? However, as this is kind of like resource intensive or like computation intensive like services we are designing, that's why we need like multiple backend services or backend hosts. So we need another load balancer in front of our backend services, which could be internal load balancer, because in this load balancer only our front end service will be able to hit. We don't accept like a public or like a request from public internet. Then when the request come to backend will do some processing and store some data in the database. So what is the most complex part in our system here? So all the things are kind of like a simple thing we know about scaling and other stuff. Frontend will receive the request and forward it to backend. However, this backend part is the most complex. So this is kind of a black box. We need to think about it. When a request lands in backend, what will we do with this, right? So let's break the giant backend service. First, we will break the backend service into two different services. One of them is like metadata service. So metadata service basically store and maintain queue and message metadata. Say for example, which user owns which queue, what messages are coming to the queue, or something like some queue setup related stuff are stored and maintained by this metadata service. Then another service would be the message broker. This is technically the main message queue service we'll be designing. It will handle actual message storing and processing things. So the process and store actual messages are kind of done by our message broker. Let's try to dive deep into the front-end service. Front-end service basically forwards the request to our metadata service and message broker. Say for example, the front-end service does the basic authentication authorization. It also routes the request to our backend and message broker service. The create queue is basically done in the front end, and when front end creates the queue for the first time, it actually maps the queue to some message broker backend host also. Now let's dive deep into the metadata service. Metadata service basically stores the queue metadata into the database. It's basically a caching layer in front of our database, and it handles all operations related to queue attributes. In the metadata service, we have multiple hosts to handle the incoming load. Now, when front-end service talks to metadata service, it needs to choose the metadata service host. So we have multiple hosts. How does front-end decide who is to talk to, right? So we can do a QID to host ID mapping. Say for example, Q1 will be mapped to host 1 and Q2 will be mapped to host 2, right? And we can do some simple hashing. Whenever a request comes to frontend, if the QID is Q1, that request will be forwarded to host 1, something like this. However, if the number of queues are like a lot and hosts are coming up and down frequently, this normal hashing does not scale. And we have some issues with that. That's why we can take the advantage of the consistent hashing. So consistent hashing kind of a complex thing, and in this lecture we won't go into the details of it, but consistent hashing will help us to choose the or map the queue to our metadata host easily. We have another lecture on this topic, consistent hashing, in the same playlist. You can also watch that. Let's dive deep into the message broker service now. So for send message, it basically stores the message. That's the simple thing. And for receive message or read message, it returns all the unread messages to the consumer. Now the question is, how can we store the messages better, right? So we need to store the message so that we can return this to our customer faster and easily. So there are a couple of options. One thing is like database over the network. Another thing is local file system, or it could be local embedded database, which almost gives kind of similar performance like local file system. So before talk about that, I would suggest everyone to read the Kafka paper, like a distributed messaging system for log processing. They basically utilize the file for storing the queue messages. We can also utilize something like WAL, which is known as like write ahead log. It's a basically log file where we can write the things and return from there and keep some pointer how far we are reading, something like this. But for our system design, I would suggest we will go with something simple like embedded local database, something like this, which almost gives similar performance like file, but also give us some easier mechanism, something to handle our database operations. Now the next question is how to ensure no data loss. When a request is coming and front-end service giving us the data in our message broker service, we can keep some backup. Say for example, after writing to our local host or local file system, the message broker will write a backup copy to the message broker 2 and another backup copy to message broker host 3, right? And whenever we receive a request, it will keep waiting until we hear back from these two hosts. When all the three writes is successful, finally we will be returning a success to our front-end service. Now there is another question: what if the whole data center goes down? So for example, we have 3 backup copy total, right? So what if the whole data center goes down? Then technically our data will be lost. That's why we can utilize the concept of cluster here, like broker cluster, and rather than keeping all the host or data backup data into same data center or availability zone, we will distribute them in different centers. Say for example, we will maintain a cluster of 9 hosts. We can choose either 3 hosts, 6 hosts, or 9 hosts, but in this example I have shown 9 hosts, right? Whenever a request come to like one of the hosts, say for example broker 1, then rather than copying them into hosts into the same data center, we will choose 2 different hosts from 2 different data centers or 2 different availability zones. Say for example, in broker 1 we will store the first backup copy in broker 4 in a different data center 2, and another copy will go to broker 9, which is in data center 3. This way we can achieve like high availability. Even if 1 or 2 data center totally goes down, we still have possibility that we will have backup data in another data center. Let's think about the placement strategy. We have multiple clusters, right? Here in example, I have shown only 2, but we might have 2000 or 200 broker clusters based on our scale, right? So when front-end service gets the request, it needs to decide where to route the request, which broker cluster should receive the request, right? So the question is, how does front-end service choose broker clusters, right? There is also another question: how does a broker host choose backup host? Because in previous slide we have seen that one broker host actually keeps 2 backup copies in 2 different hosts from 2 different data center. So how does the broker host actually choose its backup host? So to answer this question, we can introduce 2 new services, and one of them is health service and another is placement service. Every host basically reports their health data or health metrics to our health service, and the health service publishes this health data into our observability solution as well as in our database. Whenever our placement service receives a request from our front-end service, it basically first gets the health data from health service for all the hosts or clusters. And after that, it returns a set of healthy clusters to the front-end service. Similarly, when a broker host request for like backup host, placement service first read the data from health service, identifies the healthy nodes in the same cluster, then returns to backup broker host to the caller. Now again the same question, how placement service actually does the mapping here. So definitely we have some health data from where we can identify which hosts or clusters are healthy, and after that we can take advantage of consistent hashing similar way just to map the incoming queue to available healthy hosts or clusters. Let's try to dive deep into the placement service a little bit more. So placement service is the main component for auto scaling here, and load actually depends on queue uses. Say for example, some queue will have like only 200 requests, and some queue might have like 20 million requests per hour or per minute, whatever, right? So the load actually depends on the queue uses and queue size, something like this. So if a queue is getting throttled or need more capacity based on their metrics, the placement service first attaches new broker clusters to the queue. That means if the Q1 had like 100 clusters or backend or broker clusters attached to it, and we are saying like it's almost utilizing 100% of the clusters from the TPS and other metrics, then we will attach another 50 like extra 50% new clusters to the Q1 so that it does not fail and keep processing. Another thing is if queue is underutilizing assigned clusters. Say for example, after some time we realize that okay, now Q1 has kind of 150 queues assigned to it, but it's almost utilizing 10% of them, right? So we need to free the clusters assigned to Q1, and for that first we mark the cluster as read only. The reason is like we cannot just immediately take back the clusters, because on those clusters maybe we have data already which are being processed for that queue. So we first mark the cluster as read only. That means if any new message comes, so those will not be written on those clusters. And whenever all these data are kind of read out of that queue, read only queue, we can remove the tag or mapping from Q1. That means finally we will have only the queues which are needed for processing that Q1 load. So if one host in a broker clusters become unhealthy, placement service marks the cluster as read-only first. That means say in a broker cluster, if we have 1, 2, 3, 4 different broker hosts, and if one host becomes unhealthy like this one, then the whole cluster will be marked as unhealthy, and after some time we will mark that as read only. That means no new queue or data will be written to that specific cluster, and later we will load a new cluster with like 4 different hosts, and eventually this one will be taken down later. Let's talk about the consumer side now. Consumer calls the read message API providing the queue ID. They give like, hey, this is my queue ID, give me the data, right? And if we have any data available, we just return them. If it's one-to-one or point-to-point queue, that means one producer, like we have P1 is sending data to Q1, and we have consumer 1. If it's one-to-one or point-to-point queue, we set visibility is equal to false after a successful read. Say for example, in a queue we have data here, right? So after reading this much data, like C1 is here, read this, then read this, we set visibility is equal to false rather than deleting the message. So that means data will still be there, but it won't be visible to the consumer. Message is deleted only after expiration of retention period. And whenever the retention period expires like 24 hours or 2 days or 3 days, data will be deleted finally from the host. Unless customer calls like delete messages API explicitly. In that case, we will be remove them totally from the queue. Let's talk about HTTP polling and HTTP long polling. So consumer keeps calling us at a fixed interval, right? So say for example, consumer is calling us like every 3 seconds. and first time we don't have data, we are returning empty responses. Again we are returning empty responses, and after some time maybe we got some data and return those data. So that means customer keeps calling us and we are just returning empty responses, right? Sometimes maybe that is not the ideal practice customer want. So we can take advantage of like HTTP long polling. What it does, it basically gives us a time. Say for example, customer is calling us, hey, do you have any data? If not, we don't return actually empty response. We don't return empty response. Rather, we wait a little bit. Say for example, 10 seconds or 15 seconds based on the setup. Whenever data arrives within this time, we return data immediately to customer based on some settings. We have another lecture on this HTTP polling versus HTTP long polling in this same playlist. You can also watch that for better understanding. Bonus question: how to handle read for multiple consumers? So we just talked about only one consumer is reading. What if we have multiple consumers or we want to support that scenario? So Apache Kafka actually let the consumers handle the pointer for how far they have read. That means every consumer actually maintains their pointer. We can also do something on our side like maintain a queue, consumer and pointer mapping. Something like in this queue one, this consumer one has kind of read up to this point, right? P1, pointer 1. We can also maintain something like this and do some custom implementation on our side. So we are not going into the details of this today. Hope this gives some sort of idea about the implementation of distributed message queue. Thank you for watching.